Hello, this is Mrs. Poland. We are in lesson 2.06 in AP Statistics, and in this video, I'll be going over the coefficient of determination. We represent the coefficient of determination with a capital R squared. So below is the formal definition of the coefficient of determination. The coefficient of determination is the fraction of the variation in our y values that is accounted for by the least squared regression line of y on x. That definition can be a little confusing, so I'd like to go over an example. So let's go back to our example where we're looking at the relationship between attendance and scores. Notice that our test scores, look at all these y values on the dots, are varying from 31 to 50. So we have lots of variation between those y values, those test scores. How much of that variation can be attributed to attendance versus other factors that may also influence performance on a test. So what are some examples of the other factors? They could be natural ability, it could be past test performance, the amount a person studies, past courses, and I'm sure we can continue coming up with a long list of these other factors. So the coefficient of determination is looking at how much of the variation in our test scores is due to the variation in attendance as defined by our least squared regression line. R is actually R squared, or the coefficient of determination, is actually the square of our correlation coefficient. So if you recall, our correlation coefficient tells you the strength and direction of that relationship. So if I have R as 0.91 and I'm trying to calculate my coefficient of determination, all I would need to do is square R and I would get 0.83. So 83% of the variation in whatever y value I'm looking at is due to that least squared regression line based on R, whatever x variable I'm manipulating. Since R is between -1 and 1, and I'm squaring these values, so I'm always going to end up with positive values, that means my coefficient of determination has to be between 0 and 1. So if you look to the left at this diagram, if you have a correlation coefficient of 1 and you square it, the coefficient of determination is 1, and that would be considered a perfect fit. Every single point, every single data point would actually be on the line of best fit. That's true also if R was -1. The coefficient of determination would be 1. That would be a perfect fit. As you get closer and closer to 0, the fit becomes weaker and weaker. Now, we could calculate the coefficient of determination by hand, and I'm going to add another video to the folder that goes into detail about how this formula is used. I'm first going to upload a different video and then I'll create my own. But for now, I just really want you to have an intuitive sense, and I want you to be able to understand what the AP exam would expect from you. So the AP exam, although they provide the formula to you, really expects you to use technology to calculate the coefficient of determination, and they expect you to interpret it. So we're going to go back to the example that we've been using the past few days. So here in example 1, we see the actual data. So you can follow along and enter the data into your calculator. And this is the r squared is much easier to calculate than s. And so you would open up your data page, and the easiest way to get the r squared value is just from the calculator function. So you're going to go Control Page, add a calculator, hit Menu, Statistics, Stack Calculations, and we're going to do we're going to do option 4, Linear Regression. Our explanatory variable is, I called it 10. And our y variable, hold on, I have to slide down, is score. And I hit OK. So this is what we first used that second day of the unit to calculate our least squared regression line. You don't have to go through that data and statistics page. Again, A is our y-intercept, B is our slope, and you see that r squared, that 0.903, 4 is that coefficient of determination, and they also give you r. Okay, so you don't have to, it's fairly easy to get. So let's go ahead and go back to our slide, and I'm going to record that value of 0.903, and we normally represent it as a percent, so 90.3%. And so we're going to use the sentence stem in order to help interpret the value. So we can say that 90.3%, actually that's a little sloppy. So 90.3% of the variation in our test scores can be explained by the linear relationship, that's that least squared regression line, with attendance. Here's example 3. So this is the backpack body weight example we've done throughout this unit. And so we're going to create the least squared regression line first. So I'd like you to go to your graphing calculator and either upload the existing data you have or type in the body weight backpack data, and I have that already. We're going to hit Control Page and add a calculator page. We're now going to create our least squared regression line by hitting Menu, Statistics, Stack Calculations, Menu, Statistics, Stack Calculations, and we want option 4. In the explanatory variable is body weight, and the response variable is backpack weight. And we hit OK, and we get the least squared regression line, and we're going to record this information. So backpack weight is 16.265 plus 0.091 times the body weight. That's your input value. So now what we're going to do is continue on, and we want to find and interpret S. S is the standard deviation of our residuals. So we're going to look at our output from our linear regression, and what happens is when you perform that least squared regression line, the calculator calculates the residual for each x value. And so we need to store that into a variable name. So you're going to go to your calculator and you're going to hit var, and you want to scroll down until you see the variable stat resid, and you're going to hit enter. And that's a listing of our vector of residuals, and we want to store that in a letter. So we're going to hit Control var. So that operates the store function, and you can use any letter. I'm going to just use M, and I'm going to hit enter. I'm going to actually go back to my data. So 1.3, mine is in 1.3 at least, and I'm going to hit M and hit enter. So that just put all my residuals into that spreadsheet program. I now want to actually calculate the mean and the standard deviation of my residuals. So I'm going to hit Control Page, add a calculator page, or I could have gotten back to the other calculator page, it didn't matter. I hit Menu, Statistics, Stat Calculations, one variable statistics, hit OK, and now I want M is where I stored my residuals. So you see I have my mean of my residuals, which is negative 3.7 times e to the negative 13. That means that there are 12 zeros in front of the 3. That's essentially such a small number, it's essentially 0. And our standard deviation of residuals is 2.1. So I can say, let me just get a pen out here, that the standard deviation of my residuals is 2.1, and it's actually 2.1 pounds. We should get the units in there. And now we have to write our interpretation. So when using the least squared regression line with, in this case, it's body weight, that's our explanatory variable, to predict backpack weight, we typically are off about 2.1 pounds. Okay. And finally, we need to find and interpret our R-squared value. And actually, our R-squared value, we don't have to do any crazy kind of calculation like we just did, because if we just went to our original output, I think I'm going to have to, our original output from our linear regression, right 2 lines above that residual variable is our coefficient of determination. So you don't have to do anything fancy. It's generated right from the output. And so we see that's 0.6315. So let's go back here. So R squared is 0. And I'm going to round that to 3 places, 0.632. But we normally express that as a percent, or the the coefficient of determination as a percentage. So let's interpret it. 63.2% of the variation can be explained by the linear relationship with body weight.